Hello students, this is Professor Anindo Das from Achievers and welcome to my lecture series on the second law of thermodynamics. In our previous lecture, we are talking about the concepts of an engine, and for that purpose we did the Kelvin-Planck statement and we found some interesting relations in context to an engine. Let me show you what we have done in our previous lecture. See, we ended up over here, we found that an engine is guided by the Kelvin-Planck statement, and for an engine we define a very important parameter eta, and eta is given by mod W cyclic by mod QH, as you can see over here. And we have also found that mod W cyclic is equal to mod QH minus mod QC, and that we have done by applying the first law of thermodynamics, and thereby we arrived at another expression of eta, and it's given by 1 minus mod QC by mod QH. And we also found that the parameter eta, the efficiency of the engine, varies from 0 to unity. That's what we have found in our previous lecture. In today's lecture, what we'll be doing, we'll be dealing with the concept of refrigerators. So in today's lecture, we'll be dealing with the concept of refrigerators. Refrigerators. A refrigerator is also a device like an engine. It's a thermodynamic device like an engine, but it is guided by the Clausius statement or C statement. I have already told that Clausius statement is written in short as C statement. So refrigerators are guided by the C statement. Refrigerators are guided by the C statement. Now again, before going into the C statement formally, at first we need to understand the free diagram of our refrigerator. So at first we need to interpret or analyze the free diagram of the refrigerator. And once we are acquainted with the free diagram of the refrigerator, we'll be able to interpret the meaning of the C statement. That's what we need to do right now. Okay, so what we have got a system like this. The system is absolutely analogous to that of the engine. You have got a hot reservoir over here, maintained at a temperature TH, and you have got a cold reservoir over here, maintained at a temperature TC, and TH is supposed to be greater than TC. These things are already known to us. Now, this HR and CR are connected by a thermodynamic entity R. It's connected by a thermodynamic entity R. This R is the refrigerator which works in the cyclic manner. So it works in a cycle. So in case of an engine, or in order to interpret the Kelvin-Planck statement, we had the same thing, the hot reservoir at a higher temperature TH and the cold reservoir at a lower temperature TC, and they were interconnected by a thermodynamic device E. E was engine. Here HR and C are connected by a thermodynamic device called R. R is the refrigerator. So the refrigerator is positioned in the same manner as the engine, but it works a bit differently. How? You see, in a refrigerator, if you want to cool something, say you are placing a bottle of water in the refrigerator. So you place the bottle within the refrigerator. So here you will be placing the bottle of water. So this is the bottle of water. So this is the bottle of water. you are placing. So you'll be placing the bottle of water in the cold reservoir that is inside the refrigerator. So what is the hot reservoir then? The hot reservoir is then the room. The room is the hot reservoir. The room in which you are placing the refrigerator is the hot reservoir. So placing an object, say a bottle of water, inside the refrigerator. So basically what you are doing, you are putting that bottle of water or that object in the cold reservoir. And what is the hot reservoir? The hot reservoir is the room itself. The hot reservoir is the room itself in which the refrigerator is placed. Now what is the sole purpose of the refrigerator? The purpose of the refrigerator is to get this object cooled down. The purpose of the refrigerator is to get this object cooled down. And in order to meet that purpose, what is needed to be done? In order to meet that purpose, it is needed to withdraw heat from the cold reservoir. It is needed to withdraw heat from the cold reservoir. So let QC amount of heat is being withdrawn from the cold reservoir. Let QC amount of heat is being withdrawn from the cold reservoir. So that the object inside the cold reservoir gets cooled down. So you have to withdraw heat from the cold reservoir, from the object that you are placing inside the refrigerator, so that it gets cooled down. So you're withdrawing heat from the cold reservoir. And where the heat will be transferred? The heat withdrawn from the cold reservoir will naturally be transferred to the room. The room is the hot reservoir. So the heat is transferred from the refrigerator box to the room. You're transferring heat from the cold reservoir of the refrigerator to the room. The room is the hot reservoir. So you're transferring QH amount of heat to the room. Mind it, the exact amount of heat withdrawn from the cold reservoir is not transferred to the room. If you are withdrawing QC amount of heat from the cold reservoir, you are not transferring QC amount of heat to the room. You are transferring some other amount of heat to the room. That is denoted as QH. Why? Because this refrigerator cannot work itself. This refrigerator cannot work itself unless and until it is supported by some external agency. This refrigerator cannot work itself unless and until it is supported by some external agency. So in order to withdraw QC amount of heat from the cold reservoir, it is needed to be supported by some external agency. It is needed to be supported by some external agency. So some external work, W cyclic, is needed to be done on the refrigerator so that it can withdraw QC amount of heat from the cold reservoir and transfer some other amount of heat to the hot reservoir, and that is denoted as QH. So now we can write down the formal statement related to this particular thermodynamic entity refrigerator, and that is nothing but the C statement. So let us pen down the formal C statement. It is impossible for any refrigerator to withdraw heat from the cold reservoir and transfer it directly to the hot reservoir without being aided by some external agency. Let us ponder into this statement. Let us ponder into this statement. If we ponder into this statement, we see that it is impossible for any refrigerator to withdraw heat from the cold reservoir and transfer it directly to the hot reservoir. You can't just withdraw QC amount of heat from the cold reservoir and transfer it directly to the hot reservoir. That means you can't just withdraw QC amount of heat from the cold reservoir and transfer that amount of heat to the hot reservoir. That is impossible. In order to do so, the device has to be supported by some external agency. In order to do so, the device has to be supported by some external agency. The device has to be supported by some external agency. And that is nothing but W cyclic. That is nothing but W cyclic. Okay. So from this free diagram, we develop the mathematical statement in context to the refrigerator. So let's do that. I have hot reservoir, you have cold reservoir. You have a refrigerator like this. The hot reservoir is maintaining a temperature of TH. The cold reservoir is maintaining a temperature of TC. Now, what is happening over here? QC amount of heat is being withdrawn from the cold reservoir, and QH amount of heat is being transferred to the hot reservoir, and W cyclic is the amount of work that is being done on the refrigerator. So this much is pretty clear to all of us. Okay. So far so good. Now, you have to understand a few things over here. Let us draw the free diagram for the engine. The free diagram for the engine is represented like this. You have hot reservoir, you have cold reservoir, and the engine was connected like this. Now, what was happening in case of the engine? In case of the engine, we found that QH amount of heat is being withdrawn from the hot reservoir, and QC is being transferred to the cold reservoir, and W cyclic is being done by the engine. And we found two important relations. We found eta to be equal to mod W cyclic by mod QH, which is again equal to 1 minus mod QC by mod QH. Also, we found that mod W cyclic is equal to mod QH minus mod QC. So we found these things. And we also remember that this mod W cyclic was the output, and this mod QH was the input. And this eta, it was limited between 0 and 1. So this is what we have done in our very first lecture. We are acquainted with all these things. Okay. So now let us interpret this free diagram once again in the light of the first law of thermodynamics. So we are going to interpret this free diagram of the refrigerator in the light of the first law of thermodynamics. Okay. And here this refrigerator is our reference. Okay. So let's check out. By first law, we all know that Q cyclic plus W cyclic has to be equal to 0. Q cyclic plus W cyclic has to be equal to 0. Now we all know that This Q cyclic is comprised of two terms, QH, QC, and W cyclic will remain as it is. This is 0. So far so good. Now, we need to make the sign corrections. What should be the sign of QH? You see the arrow is away from the refrigerator. The refrigerator is the reference and the arrow is away from the refrigerator. So QH must be negative. What about QC? You see the arrow of QC is towards the refrigerator. The arrow of QC is towards the refrigerator. So if the arrow is towards the reference, then it's positive. What about W cyclic? You see again the arrow of W cyclic is towards the reference refrigerator. So it's again positive. So if QH is negative, then QH can be written as minus mod QH. If QC is positive, then it is written as plus mod QC. If W cyclic is positive, then it is written as plus mod W cyclic. And the entire thing is equal to 0. QC is negative, QH is negative, that's why it is written as minus mod QH. QC is positive, that's why it is written as plus mod QC. And W cyclic is positive, so it is written as plus mod W cyclic. Okay. So what is the expression of mod W cyclic? The expression of mod W cyclic is given as mod QH minus mod QC. So the expression of mod W cyclic becomes mod QH minus mod QC. Okay. And students, you see, there is a very close resemblance between these two expressions. There is a very close resemblance between the expressions exhibited by R and E. E exhibits mod W cyclic equal to mod QH minus mod QC. R also exhibits a similar type of an expression. A similar type of an expression. A similar type of an expression. We will reveal the reason later. We will reveal the reason later. It's not our objective right now to reveal the reason. We will reveal the reason later. Let's move on. You just keep this thing in mind. There is a very close resemblance between R and E in terms of the mathematical expression mod W cyclic equal to mod QH minus mod QC. You would answer, why is there this sort of a resemblance? That would be answered later. But I think you have noted this particular point. This is a point to be noted. This is a point to be noted. A point to be noted. Okay. Now one more thing has to be understood. One more thing has to be understood. You see, can we define the efficiency of a refrigerator? Can we define the efficiency of a refrigerator? Is it possible to define the efficiency of a refrigerator? Efficiency is defined as output divided by input. So can we define the efficiency of a refrigerator? Is it possible? Is it possible to define the efficiency of a refrigerator? Answer is no. Why? Because you see, in this case, mod W cyclic is the input and the output is mod QH. Mod QH is the output. You are giving mod W cyclic and you are getting mod QH. So the output mod is mod QH and the input is mod W cyclic. Now which one is greater? We know directly from this equation that mod QH is greater than mod W cyclic. Mod QH is greater than mod W cyclic. So the output is greater than the input. Mod QH is greater than mod W cyclic. So output is greater than input. So the output is greater than input. If the output is greater than input, then output by input is obviously greater than 1. So the efficiency will become greater than 1. Or in percentage it is greater than 100%. I think this is clear to you all. Because in case of refrigerator, this particular term mod QH becomes the output, and this particular term mod W cyclic, it becomes the input. So it is just the reverse. So it becomes mod QH by mod W cyclic. And if this is less than 1, then that eta that is directly defined for the refrigerator would obviously be greater than 1. In percentage it is greater than 100%, and that is physically not possible. So one can say that we cannot directly measure the efficiency of a refrigerator. This is very important. If we directly measure the efficiency of a refrigerator direct from the free diagram, then what is going to happen? Then we will see that the parameter eta is becoming greater than 1, or in percentage it is becoming greater than 100%, which is physically meaningless. So it's not possible to evaluate eta directly from the free diagram exhibited by the refrigerator. That is not possible. So the next question arises is, can it be possible to determine eta for a refrigerator at all? Is it at all possible to determine the efficiency of a refrigerator? We have understood that it is not possible from the direct analysis of the free diagram. It is not possible from the direct analysis of the free diagram. That's known to all of us. Now our next question is whether at all it is possible to evaluate the expression of eta somehow for a refrigerator. We know that it is not possible directly. But is there some other means by which you can develop the expression of eta for a refrigerator? In order to answer this question, you must ponder onto these two diagrams once again. What do you see? What do you see? Let's check. For refrigerator, QH is in this direction, in the upward direction. QC is in this direction, in the upward direction. And W cyclic is in this direction, towards the refrigerator. What happens for E? For E, you see all the arrows are reversed. This arrow is in the downward direction, so there is the reversal of arrow. This QC arrow is in the downward direction, so again there is a reversal of arrow. And this W cyclic is in this direction, it is the away from the engine, and it is towards the refrigerator. So you see, for the engine and for the refrigerator, what do you observe? What do you observe? What do you observe? You observe that for the engine, QH occurs in this direction, but for the refrigerator, it is in this direction. For the engine, QC is in this direction towards the sear. And for the refrigerator, it's away from sear. For the engine, the W cyclic is away from E. For the refrigerator, W cyclic is towards the refrigerator. So basically, these two can be interconverted by reversing the arrow. Interconvertible by reversing the arrow. Arrow means direction. So interconvertible by reversing the direction. But there is a condition. You can't convert any E to any R. You can't convert any E to R or vice versa, any R to E. Although it is apparently like that, just you reverse the direction of the arrow, you will be converting an engine to a refrigerator. It is quite evident from these free diagrams. But logically, it is not possible. It is not possible for any engine to be converted into a refrigerator just by reversing the arrow. Just by reversing the arrow. Just by reversing the arrow. So it is interconvertible by reversing the direction under the constraint. There is a constraint. Under the constraint, a very simple one. Under the constraint of reversibility. Under the constraint of reversibility. I mean to say that in order to convert E to R and R to E, both the entities must be reversible. If the engine is not reversible, you cannot reverse the direction of the engine and convert it into refrigerator. Similarly, if the refrigerator is not reversible, then you just cannot convert the refrigerator directly to the engine just by reversing the direction. So in order to convert a refrigerator into an engine or an engine into a refrigerator, we must ensure that each of them is reversible in nature. That is the fundamental requirement. So what we can do for the refrigerator, we directly cannot measure efficiency. So what we can do? So if R is reversible, it can be inverted into E. If R is reversible, you can always convert it into E. If R is reversible, you can always convert it into E without any hesitation. If R is reversible, you can always convert it into E. There is no problem with that. Again, we can determine the eta of E directly. So what is the trick we are applying? We know that we cannot evaluate the efficiency of R directly. Okay, that is known to all of us. Because in that case, the output will exceed the input and efficiency will be greater than unity, and that is not possible physically. Okay. So, what is the remedy? If the refrigerator is reversible in nature, then we can reverse the direction of the refrigerator and convert it into an engine. That we can do. Now, once it is converted into an engine, we can evaluate its efficiency directly. Once it is converted into an engine, we can always evaluate its efficiency directly. So thereby, we can evaluate the efficiency of a refrigerator not directly, but by converting it into an engine. So in this way, we can calculate the efficiency. So in this way, eta of R can be determined. Okay? Understood? So this is the thing we want to interpret in case of a refrigerator. So for a refrigerator, we cannot determine the parameter efficiency directly. But is there any other parameter that can be determined directly with respect to R? We know we cannot determine eta directly for R, because in that case eta will become greater than 1, which is physically meaningless. That's why we would convert R into E provided R is reversible, and then we will indirectly determine the efficiency of E, which will in turn be equal to the efficiency of R. That is understandable. But now my question is whether we have any parameter or not which can be directly measured with respect to R, and that is relevant to the working principle of R. And there is a parameter called COP. The acronym stands for coefficient of performance. Coefficient of performance, which is denoted as eta dash. So for a refrigerator, we'll be determining COP or eta dash. Okay. Now we need to understand the meaning. So for that purpose, let us draw the free diagram once again. So this is the structure, and we know that it works in this way. Here you have got HR at temperature TH. Here you have got cold reservoir at temperature TC. QC is withdrawn from the cold reservoir, QH is transferred to the hot reservoir, and mod W cyclic is being done on R. So these things are pretty clear to all of us right now. And also we are acquainted with the fact that mod W cyclic is equal to mod QH minus mod QC. Now coefficient of performance is a parameter which is a bit different in context to eta. Eta stands for the ratio between output and input, whereas coefficient of performance stands for the ratio between performance and input. So at first let us mark the input and output. This was the output. This is the input. And QC, this is the performance. Now you have to understand this meaning. Why QC is said to be the performance? Because the fundamental working of a refrigerator depends on QC. The fundamental working of a refrigerator depends on QC. Because you are placing an object inside the refrigerator. You are placing an object inside the refrigerator. You are placing an object inside the refrigerator. And that object is to be cooled down. and that object is to be cooled down, and that object is to be cooled down. For that purpose, you need to withdraw heat. You need to withdraw heat from that object. And for that purpose, this QC term becomes utterly important. And that is the sole purpose of a refrigerator. So this is the performance of the refrigerator. And by definition, COP, which is equivalent to eta dash, is defined as the performance, that is mod QC, divided by the input mod W cyclic. So you have performance in the numerator and input in the denominator. So you have got performance in the numerator and input in the denominator. Okay. Okay. So eta dash is equal to mod QC divided by mod QH. Okay. Now mod QC can be written as, from this equation you can see mod QC is mod QH minus mod W cyclic. It's quite evident. So you replace mod QC by mod QH minus mod W cyclic divided by mod QH. Okay. Okay. So what we are getting? I have made a mistake over here. This is mod W cyclic. In the denominator you have mod W cyclic. Wrongly I have written mod QH in the denominator. It should be mod W cyclic. Okay. So it is mod QC by mod W cyclic. And now you are replacing mod QC by mod QH minus mod W cyclic. That is quite evident from here. From here you can always write mod QC equal to mod QH minus mod W cyclic. That is being replaced over here. So you are getting mod QH by mod W cyclic minus 1. And students, we all know that eta is equal to mod W cyclic by mod QH. So mod QH by mod W cyclic is nothing but 1 by eta. So mod QH by mod W cyclic should be 1 by eta. So mod QH by mod W cyclic is nothing but 1 by eta. So we have established a relation between coefficient of performance and eta, and it is given by eta dash equal to 1 minus eta by eta. So this is the relation between the coefficient of performance and the efficiency. Okay. Thank you all students, and bye for now.